Hi, you calculus cool cats. Today we're working on integration by parts. So it's about finding an antiderivative and using integration by parts. It's a technique that can be applied to a wide variety of functions, but it's particularly helpful when you have an integral involving a product of two functions. So integration by parts is the first secondary resource that you should consult if you can't find an integral with one of the basic rules. Integration by parts is based on the formula for the derivative of a product rule. So I've already got something kind of set out here for you. If you look, we have the integration by parts formula. Let me just cut that out of there. So I've got, if you consider that it's based on the formula for the derivative of a product rule, then if I take the derivative of a product rule of a product, then I get this expression. So in the first line, but then if I take the integral of each side, so that means I take the integral of the derivative getting back to u times v, and that's equal to the integral of u dv. I'm sorry, I missed my plus sign there, plus the integral of v du. So if I do a little manipulation here, I would do uv minus the integral of v du would be equal to the integral of u dv. Now, as it turns out, we want to solve for the integral of u dv. So you can see I'm going to put that on the left-hand side. And the integral of u dv is equal to uv minus the integral of v du. Or if you look at this in the table, with integration by parts, this formula just didn't drop out of the sky. So it's really based on the product rule. If you would be our functions in x, functions of x, and have continuous derivatives, then the integral of u dv is equal to uv minus the integral of v du. So the formula expresses the original integral in terms of another integral. Depending on the choices of u and dv, it'll help you to be successful to integrate. So guidelines for this are, you want to let dv be a function that can be integrated, and then you want u to be a function whose derivative is typically simpler. So if I have a u of x squared, then the du is 2x dx. 2x is a lower power than is x squared, so that's kind of where you want to head with this. So we're going to start off with the first one, and there's some little hints I'll give you down the lane, down the road. But let's just do the first one, and we'll get through a couple of these, and then we'll get to that. So if I look at this, I'm going to say I'm going to let u, which is u has to be that should have where the derivative can't talk today. So u is equal to, I'm going to make it x because the derivative du is equal to just 1 dx. So, and then if I pick dv equal to e to the x dx, then my v is going to equal, picture yourself taking the integral of both sides of this, but you're not going to need to put the plus c on it. It's just going to be v is equal to e to the x. So now I have my u and my v. I'm going to take the 1 out of this right now. I have the integral, and let me move this down just a little bit, because I'm going to put the rule in too, because we're going to follow this rule strictly. So the integral of u dv is equal to uv minus the integral of v du. So I'm going to take the information that I've already set up, and I'm going to say my integral here of x e to the x dx is equal to my u, which is x, my v is e to the x. I'm using these two things over here, my u and my v. And then I have minus sign. That's always something you have to be clear about when you're subtracting quantities, minus the integral of e to the x dx. So as it turns out, this one is fairly simple. I'm just going to write it on both sides here. So we get the integral is equal to x e to the x minus e to the x, but then we have to remember our arbitrary constant in the end, and there you have it. There it is. There you go. Oh, kind of fell on that one, so I'm gonna have that. I'm just gonna go ahead and change the style here so there's no fill. Boop. All right, and there's our answer. Okay, moving along to the next one. All right, so there's our first integration by parts. Now remember that you have to be able to take the derivative. dv has to be integrable. And I look at this one and I've got two functions. I'm gonna make this a little bit bigger. So here in the functions, we don't know the integral of ln of x. So we're not gonna pick that for our dv. So in this case, I'm gonna say my x squared, oh, I'm sorry, wrong color here. I'm going to highlight that with green, and then I'm going to highlight this purple. So I'm going to pick my u to be equal to ln of x, where my dv, I'm going to make that equal to x squared dx. So remember, the dv, you're integrating on both sides. So get a little highlighter in here, lime green highlighter. So dv is then equal to the x squared part of the integrand. So here we go. My du, oops, slide a little bit, go back to blue. So I have, if I want to find this integral, I'm going to go ahead and write the formula down again. The integral of u dv is equal to ub minus the integral of v du. It's kind of mechanistic, this whole lesson is. So here we go. I need to make a little bit more room for my table to continue it. I need my du. So my du, the integral, or the derivative of ln of x is 1 over x dx we need. And then over here, we're going to have v is equal to x cubed over 3. Plugging in then, we have the integral of x squared ln of x dx is then equal to uv. So we're going to have, I'm going to put the x cubed, the v out front, x cubed over 3 times ln of x, just using the commutative property. We usually like the polynomial out in front of the logarithm. And then minus the integral of v du, so that's x cubed over 3 times 1 over x dx. So what we'll be able to do is simplify that integral. So now we have x cubed over 3 ln of x minus, we're going to simplify, so now we have the integral of x, you could put the 1/3 out front though, so it would be minus 1/3 the integral of x squared dx. So easy to integrate now. We have x cubed over 3 ln of x minus, we're going to have 1/3, and it'll be 1/3 times x cubed over 3. And then the arbitrary constant plus 3, x cubed over 3, as we are integrating x squared. And we're going to then simplify. Sometimes we like to take a common factor, and we're going to take the common factor of x cubed over 3. We're going to pull that out in a, take the two terms and say this is x cubed over 3. And keep in mind, we don't know what c is. And then times the quantity ln of x minus 1/3. And then that would, of course, change what the c is, but sometimes we like to do things like that. Doesn't matter. And we could still write it as x cubed over 3, or put a little or in here. So here's our integral, or x cubed over 3 ln of x minus x cubed over 9 plus c, and we could have that as our answer, either or in this. Okay, that's 2 integration by part problems down. And now one more that we have for today is we're going to handle a repeated use of integration by parts to find the integral of x squared sine x, right? So it is x squared sine x. So, and this will be the last of the indefinite integrals. So here we go. I'm going to start off and I'm going to say, okay, the derivative, I'm going to make my u differentiable, which is x squared. And in this case, somebody might say, well, sine is also differentiable and x squared and sine are also integral. So we have u is equal to x squared, and then we have dv is equal to sine x dx. So we get our du is equal to 2x dx, and we get our v is equal to, now remember, you're integrating here, and sometimes students will forget that. When you're integrating, you have to remember that you have that sine thing, right? So undoing sine, the v is going to be equal to negative cosine x. Now take the derivative of cosine, and you would get negative sine. So you need that negative sign in for the integral or the antiderivative of sine x to get to cosine x. I often tell you guys to use think cycles with those just to make sure you get the sign right. Okay, so we're going to do this one more time. So now I'm going to leave out the formula here. We'll go a little bit with that. So we have the integral of x squared sine x dx is then equal to, so it's equal to uv. So we have our u and our v. Here's our u and here's our v. So we're going to say x squared, bring the negative sign out front, cosine x minus the integral of v, which is negative cosine. So I'm going to say plus now cosine x. I'm going to make that, let's take a step back from that. So I want to make sure I get everybody in here because somebody might have just looked away. Negative cosine x v du, which is times 2x dx. Okay, so we have this is equal to negative x squared cosine x, and it will then be plus the integral of 2x cosine x dx. So now we have another integration by parts. So I'm going to scroll up just a little bit. I feel like I'm going downhill on this problem. So I'm going to say u again. Now I'm going to set it up over here. So I have u is then going to be equal to 2x, and dv is equal to cosine x dx. So my du is 2 dx, and my v is then going to be equal to sine x. So there is my work, and I'm going to skip down here. So I have the integral of x squared sine x dx is then equal to negative x squared cosine x. And then it's going to be plus, so now I have to do my uv. So here's my u and my v, that will come first. So it'll be 2x sine x. And then my v du, the integral of v du, let me scroll just a little bit, minus the integral of v du. So that's going to be sine x times 2 dx. So that seems to work out nicely. Negative x squared cosine x plus 2x sine x, and this will be minus 2, the integral of sine, the antiderivative of sine, then is cosine. So it'll be, or negative cosine. And then I have the arbitrary constant. So my final answer, the integral of x squared sine x dx, is negative x squared cosine x plus 2x sine x, and then it'll be plus 2 cosine x plus, ooh, accidentally hit something there, plus c. Sorry about that. There's so much going on. So here is my answer for that problem. Sometimes that works, and I'm not quite sure why I get it sometimes and why I don't others. Here we go. And there is your answer. So applying integration by parts is just a new technique for us to handle an integral of a product of two functions. So I hope this was helpful. I'm not sure the lighting was very good. I'm just getting used to using Zoom for making videos, but it seemed like a great avenue. The next video is going to be on integration by parts, but doing definite integrals. And then I have a neat little trick for you. And we'll have a video in today's class as well. I should have told you, dang. All right, see you back on the second video.